Hello, everybody. So we're going to kind of take a little bit of a different direction in this video, though it is still related. One of the things we've been doing with statistics, right? When you think about hypothesis tests, for instance, is trying to see the relationship between certain variables, right? Did doing something or being in a new location change the behavior of something or the characteristic or proportion of something, right? So what we're going to look at now is a little bit of how things can be related, and then if we can sort of characterize that relationship. So we gotta look in a little bit different direction for a moment. We're going to talk briefly about functions. All right, so it's a pretty simple concept what a function is. We usually think of we'll think in terms of x and y. You can name things anything you want, but x and y are kind of the typical ones we have. So all a function means is you have an input and an output, right? So you have some characteristic or idea that you think of as your input, and depending on what the input is, you get an output. Right, so a function could be something like each of you input your name and I can output your grade in this class. That would be a function. You each get one output, right? Or input your name and output your student number. That would be another function. Or we could input a zip code, and output the population in that zip code. Those are all examples of inputs and outputs functions. So we often use x to represent the input variable and y to represent the output variable. We usually call this the independent variable, and this one the dependent. Okay, so again, there's lots and lots and lots of examples of functions, right? If you go to ship a package, the price you pay depends on the weight of the package, for instance. And so we would think of the weight there as the independent input variable and the price as the output. Or a certain chemical reaction, how much energy it outputs might depend on the temperature at which the reaction is happening. Or if you're saving for retirement, how much interest you earn, right? If it's got a rate of interest, how much interest you earn overall will depend on how long you have it there. So your input would be time and your output is the interest that you earn, okay? There are lots and lots and lots of ways for things to be related, right? So in all those cases, I said one thing depends on another, and depending on what the input is, you get a different output. But exactly how they relate to each other comes in many different forms, right? We are going to talk about linear relationships, okay? But there are plenty of others you may have heard of, things like you can have a quadratic relationship, an exponential relationship, an inverse, let's say an inverse square relationship, right? So you may or may not have heard some of these. It's fine either way. I just want to be clear. The one we're going to talk about, linear, is probably the most straightforward relationship, but there are other relationships out there. So I don't want to imply that this is the only way in which variables can be related to each other, okay? So what does linear mean? So there's a few ways we can think about linear, but one good way to think about it is the rate of change is constant. And the rate of change, we can just define it as it's the change in output divided by the change in the input. Right, so it's just measuring if I change the input by an increment, by let's say a unit, how much will the output change by? And for linear functions, that number is the same whether you're at the beginning of the relationship or at the end of it. So for example, here's an easy example of a linear relationship. If a car moves with constant speed, let's say 30 miles per hour, and let's say it begins 10 miles from you, and it's driving away. Let's just, for simplicity, say in a straight line. Then you could say, so let's say at time 0, the car is 10 miles away from you. At time 1, meaning 1 hour later, if it's traveling 30 miles an hour, it will now be 40 miles away, right? So the change, the rate of change here is just going to be how much did the output, in this case, how far is it from you? Well, that change was 40 minus 10 over the change in the input, 1 minus 0, or 30. And if I check later, if I check, for instance, at, let's say, t equals 5 and t equals 7, right? Well, at t equals 5, let's see, it's going to be 160 miles away from you. And at t equals 7, it will be 220 miles away from you. Well, the rate of change here is going to be the change in how far away it is. So from 220 minus 160 over how many seconds or hours have passed. 7 minus 5 or 2. We get 60 over 2. We get 30, right? So we're still getting that 30 miles per hour here, right? And so that didn't matter if we looked at the first hour or between the 5th and the 7th hours, that rate of change is constant, okay? This is not always the case. Just as a little counterexample, for instance, if you were to drop a ball from 100 meters on Earth, right? If we had the input time, for instance, at t equals 0, and the output height, the height is going to be, well, at time 0, it's at 100 meters. Well, according to physics, if you go through 1 second, its height will now be, it will have fallen down to 95.1 meters, right? It's dropping. After the second, the height will now be 80.4, right? So notice in this first second, it goes down 4.9 meters. In the second, it goes down 14.7 meters, right? So there's a much different rate of change in the second than there is in the first second, right? In the first second, the average rate of change is just under 5 meters per second, and in that second, it's almost 15 meters per second, right? It's a very different situation. It's not a linear relationship because that rate of change is changing as opposed to how this car was traveling. Okay, so let's go back to focusing on linear functions. They're if you're curious, this falling ball has a quadratic relationship, but again, we're going to focus on linear. So when we talk about a linear function, there's a typical equation, or let's say a linear relationship. The relationship can be expressed mathematically with an equation of this form. So x and y are our inputs. Those things are going to be changing. I'm going to, for instance, if I was writing a relationship for this car, I can write it in this form where t would go where x is and the distance away would be y. Those are going to be changing, but m and b have special meanings. M is what we call the slope, right? And this is the amount, the dependent variable changes if you change the independent variable by 1. And more specifically, let's say, we should say if we increase. Okay, this tells us what happens if we increase the independent variable by 1. Okay, and then B, we call the intercept, or the y-intercept. I'll just call it the intercept. And this is just the value of the dependent variable when the independent variable is 0, right? So sometimes we can think of that as the beginning, right? Especially if our independent variable is time, it's where is this thing at the beginning. So for example, in this car example I just did, if I had d as my dependent variable, it's the distance the car is from me after t hours, the slope is the amount the dependent variable changes if you increase the independent variable by 1. In other words, if I change my time by 1 hour, how much farther is the car? Well, we just saw it goes 30 miles each hour. And then the intercept, where is the car at the beginning? It's already 10 miles away, right? And so this is how I was computing these numbers over here. If t equals 0, then d equals 30 times 0 plus 10, or 10. If t equals, let's say, 5, then d equals 30 times 5 plus 10, or 160. So that's how I was able to compute these numbers over here. Okay, so that's what a linear function looks like algebraically. We can also think of them graphically. So let's draw our little set of coordinate axes. So here's what we typically do is we let values on the horizontal axis represent x, or the dependent variable, and we let values on the vertical axis represent y. Oh, sorry, I wrote dependent. This is independent, and this is the dependent variable. Right? And we can graph these relationships. So for instance, if I were to, let's make a little scale here. I'm going to go by tens since, so we'll call this one 20, 40, 60, 80. And the x-axis, I'm going to go by 1 since it's moving forward in increments of 1. So we can graph a function like this, right? For instance, I know when t equals 0, the distance is 10, right? So I've gone on the independent variable, I've gone 0 units to the left or the right, and I'm going 10 units up for the dependent variable. When I move over 1 unit on the horizontal axis to 1 hour later, I should now be at 40 units high for the dependent variable. Do one more at 2 units, I should be up to 70. And if we draw enough of these points, we can connect them with a line, right? So I'm not perfect, but that would be a visual of what this relationship is, okay? And what it might come as no surprise, a linear relationship, the graph looks like a line, right? And that's always the case, okay? And these two pieces, the slope and the intercept, tell us how the line is going to look. The slope determines how steep it is, right? If my slope was smaller, right? So this one has a slope of 30. If my slope was smaller, it would be less steep, right? The intercept tells you where it hits this y-axis, right? So a negative y-intercept, the line would be down here, a positive one, it would be up here. Our slope can also be negative. In that case, the line is going down as we go left to right, right? So negative slope goes down as we go left to right, a positive slope goes up as we go left to right, and the intercept controls where it hits that vertical axis. The bigger the intercept, the higher up along the axis it hits. And so for this line, it hit at 10 and had this relatively steep slope of 30. Okay. Now, what we're going to try to do is find a relationship like this when we have data. Okay. So if we have two variables, right, we can plot the data as I just did with that car example, right? If I have my input variable, I'll just call it X for now, and my output Y, we can measure it, right? If this is something in the real world, so maybe I'm looking at the amount of medicine somebody takes, and that's the input, and the output could be how long their recovery time is, or you could look at something like the height of somebody and how often they drink water and try to relate them and see what you get. Now, what ends up happening when we get data is the world is an imperfect place, right? If I'm studying a medicine and I have 50 patients and I give them all this different amounts of the medicine and I want to see how their different recovery times are, some of the people who take the medicine might also get some extra sleep, and some people might be on a better diet, and some people might have a better natural immunity, and all kinds of different variables come into play. And so the data doesn't come out perfect. There's noise. And so instead of being along a straight line, our data might look something like this, right? This is something we call a scatter plot, right? Each of these pieces of data, let's look at one in particular. For instance, this piece here, right, represents, if this is the value A, and let's say this is some other output value B, we call this the point AB. And we do that for every input and output that we get. If I look at this data that I've drawn here, it does appear that it sort of looks like it falls on a line, right? But it's not perfect. And so what we're going to try to do is say, all right, it's not perfect, but can we find a line that's a good match to all of this data, right? And we'll see how to do this in just a minute. I want to point out that depending on what the data looks like, we may or may not be able to do this, right? So for instance, here's some data that looks like it has a good match. That's linear and positive, a positive slope. It could end up looking like this, and maybe looks like it might have a linear and negative slope relationship, but it might also look like this, right? There doesn't appear to be a linear relationship between these. This data looks actually not to be very well related at all. Or maybe it looks something like this, which doesn't look to be a great linear relationship, but might be explained by one of those other relationships that we were talking about. For instance, this one might have some kind of exponential relationship, okay? So we're not always going to be able to find this relationship, but we're gonna see when we do find it, how do we find this line and write an equation for it. That's our next job. So let's go into a little more detail with some actual data. So I'm going to share with you this plot. So what we're looking at here is a small sample of data. These are, let's see, I have X and Y. The X data, this is all in centimeters. The X data is femur length, and the Y data is height. So it looked at how long was a femur bone versus what was the total height. Okay, so I treated the femur length as my independent variable, the input, and the height as the output. This was data that archaeologists were constructing to be able to predict heights of people when they didn't find complete skeletons. So you want to find a relationship between the length of a femur bone and the height of a person. So if you're out digging in some ancient village and you find a femur bone, you can get a good approximation to the height, okay? So looking at this data, and again, this is a very small amount of data to make our job simple. Looking at this data, oops, I'm gonna zoom in just a little bit. Okay. It looks more or less linear. It's not a great linear relationship, but it looks okay. So I could draw a line that I think matches that data, okay? Actually, let me zoom out for a moment. So there are two things I can change. So I can change the slope of this line, right, to try to best match the data. And I can change the intercept, right? Notice I'm moving it up and down here, okay? So depending on which of these I choose, I get better and worse fits for the data, right? This looks pretty good right now. This looks worse to me, right? It looks like not quite as good. That looks a little bit better. This looks not as good to me. This looks not as good to me. Somewhere in here looks like a pretty good fit. Now, how do we determine which of those we should use? I'm just eyeballing it right now. And there's a process that we use that we're not going to have to compute by hand. I'm not going to go through the computation of this. I just want to give you the idea because we're going to let technology do it. It's a little bit of a time-consuming process. Here's the idea. Each of these points, right? For instance, this data point right here, let's use a better color. This data point right here is wrong, right? The line isn't correct. There's a distance between them. And this one right here has a distance between the data point and the line. There's a distance here, a distance here, a distance here. So this one's very small. This one's much further away, right? I'm moving exactly vertically because, for instance, this data point right here is the first data point where the femur length is 50.1. 32, where the femur length is 32 centimeters. And for a femur length of 32 centimeters, the line predicts a height, it looks like about 150 right here on the line, but our data says 155. So there's a difference here of 5. That's why I'm moving vertically, not sort of the shortest distance to that line, right? So each of these bars, the length of these bars is the error that this line has from the actual data, right? And if I choose a different line, right, if I were to change the slope a little bit, right, I would have to go through and redo all those lines. Some of them got worse, some of them got better, right? Let's go back to the one I just had. So depending on which line we choose, we get different sizes of these errors, right? But whenever I change them for any reasonable line, any change, it looks like some of them are going to get better and some of them are going to get worse. So what we want to do is measure the one that has the least amount of error. So one thing we could do is add them up. The problem is this area here is a positive error. Sorry, the line has a negative error here. The line has a positive error here. It's above, right? If I added them together, they would cancel out. And so even though there's big errors, we would end up with something like 0 because the negative ones would cancel with the positive ones. And so we'd end up with a very bad measure. So what we do is we take each error and we square it and we add them up. Okay. So we take this number and what we can do is use calculus to find the slope and the intercept that makes this number, the sum of the squares of the errors, the smallest, okay? And so we sometimes call this the least squares line, right? We also call this a linear regression, right? We're matching our data to a line in this case. You can do a similar thing for those other relationships we talked about, but this one's, we're just going to be doing a linear regression, okay? So the process for doing that is a bit time consuming and it requires calculus. Luckily, our systems can do it. This graphing program I have, for instance, does it for me. And here, let me erase the error bars I've drawn. And let's compare. So here's my eyeball best fit line. Let's compare that to what doing this process, finding the line that has the least sum, the smallest sum of the squares of the errors. And oops, I'm going to turn this off. Here we go. So mine was pretty close, but not exactly. This black line that's lying just on top of it, it's a bit different. I'll get rid of mine now. This is the line that has the smallest sum of the squares of error, right? And so I let the software do it for me. We're going to do an example. I'm going to show you how to do that in Google Sheets. And this Desmos also does it pretty well, but I'm not going to go through that process. I'm going to do one in Google Sheets, right? But to be clear, this line, which ended up having a slope, it's given here as 1.29 and an intercept of 109.38, is the one that minimizes the sum of the squares of the errors, okay? And this is a very, very, very common idea. So just about every piece of software will do it for us, okay? All right, let's take a look now at another set of data and how we might come up with this least squares line in this linear regression in Google Sheets. Oops. Let's stop sharing and go to, okay, so here I have a document called Cricket data. Oh, wait, I'm going to need to actually see some of those controls. Oops, there we go. So this is from an actual study. This is a small set of data from an actual study done, I think, in the 40s, where a naturalist went out and noticed, it had been noticed that crickets seemed to change the rate of chirping depending on the temperature. So they went out and recorded some chirps at different temperatures and counted the rate. And so we have temperature data in degrees Fahrenheit and chirps per second as our two different data types, okay? So I'm going to do a few things with this data. The first thing is create a scatter plot, okay? So I've selected my data and I'm going to look for insert chart. And depending, so I've already gone through this once, so Google guessed correctly that I wanted a scatter plot. It doesn't always happen, right? The first time I opened this and did it, I think it tried to do some kind of bar graph and showed me this. And so I chose from chart type over here, a scatter chart, okay? So, and I want to make sure I want my temperature to be the independent variable on the horizontal axis and the chirps per second to be the dependent variable on the y-axis. And again, the sheets guessed correctly, but if I needed to change it, you can change it over here where it asks which data is in the x-axis, which data is in the y-axis, okay? Oops, I need to go back in. So if you ever get out of editing mode, you can get into editing right there. Okay, so you might notice right now this is not a great chart because we can't even really see all of our data. So I'm going to go over to Customize. And let's start by looking at the horizontal axis, okay? So I want to change the minimum and maximum value. Now, it's nice if you can start at 0 so we don't run into these problems of sort of misleading charts where you're not actually starting at 0. Sometimes that can affect how they're read. But because the data is all, the horizontal, the independent data is all above, it looks like just under 70 is the lowest data. If I started at 0, so I'm looking at my minimum value and went up to say like 95 maybe, right? Then the data is all crunched to one side and it really makes it difficult to interpret. So I don't think that's a good choice here. So I'm going to look at my data and see that 65 is just a little bit below the highest data. I'm going to put a little more room on the right side. So now horizontally, I've got a good view of all of my data. Let's look at vertical, where I have a much bigger problem. Here, I think I can stick with 0, but I noticed that some of my data is off the screen, so I'm looking at my chirps per second and seeing that the highest is 20. So I want to go a bit higher than that. I'm going to try 25 and see how it looks. That looks reasonable to me. I can see all the data comfortably. It's not too obscured, too far away, too crunched together. It seems reasonable. You can make other choices. This is the one I'm going to make. So looking at this data, right, it doesn't seem unreasonable to imagine drawing a line through it, right? It seems to be the case that as I increase the temperature, the chirp rate is going up at a relatively constant rate, right? You can imagine recording this in the wild, all the other variables that are at play. You're trying to look at temperature, right? You go out and record one day at a temperature of 88 degrees Fahrenheit, 88.6 degrees Fahrenheit, and you maybe get one cricket chirping, and the next day you have a different cricket chirping who's just naturally a little slower or a little faster. So you're going to get little other variations in this, but there does seem to be a general trend. That's another word we give to this, this regression, is a trend line. So I don't want to try to guess what that line is. I'm going to use my software to do it for me. So we're going to do it in a couple of different ways. What I need to know what that line is, remember my linear relationship is going to look like, let's say here, let's go with temperature and C for chirp rate. The chirp rate is going to be some constant M times the temperature plus B, right? So M and B are the numbers I'm looking for in my linear regression. I need the slope and the intercept, and then C and T are my variables, right? T is the independent variable. I input a temperature, I output a chirp rate. The chirp rate depends on the temperature is how I'm thinking about this. So I can use this software to come up with that. So I'm gonna use a command here. So the command, start with equal, and then I do ln, and it already predicts what I want, linest, and you can see underneath it says best fit linear trend via least squares, meaning this is the best fitting linear relationship using the least squares method, right? There are other methods out there. This is the most popular in my experience, but they're just letting you know that that's the one they're using. So I hit that. So now I have to tell it what to do this linear trend to. So I need to select first. I believe it does the output data first. So you can type it in, or I can just click and then shift click. Notice it puts in C3 to C17. That's telling it this is the dependent variable. Then I use a semicolon, and I got to tell it what's the independent variable. Close my parentheses. And there's two numbers that show up, okay? It just automatically puts two numbers in. And what these numbers are, the first number is the slope. The second number is the intercept, okay? Oops. Let's pretty this up a little bit. I like it center, justified. I don't think we need all those decimal places. Let's do 2 decimal places. Okay, so there's let's do 3 decimal places. I just remembered why I want that. We'll see in just a moment. Okay, 3 decimal places, and I always like to give a little style to the header. Okay, so here's a little table we have with the slope and the intercept of the least squares regression. In other words, the line that we want would look like C equals 0.203 T plus 0.459. right? In other words, if you input a temperature, multiply it by this number, and add this to it, you should get a good approximation to the chirp rate, okay? So that's one way we can get the slope and the intercept. We can get it computed right there. We can also, and it would be nice to be able to see this on our chart. So let's get rid of some of this. Maybe I'll keep this and just move it over here for now, maybe down here, just in case we decide we need it. Okay. It would be really nice to have this line on our chart. And luckily, it lets us. So if we look under series, notice there are several things we can click on. I'm going to turn on the trend line. And so it drew the line in. We've already computed the slope and the intercept, but maybe we want this to be available on our chart. And so under label, I can tell it to use the equation, and it writes 0.203 times x plus 0.459. That's why I rounded to 3 decimal places. We see that it matches, right? They're using x because they don't know what I want to call this stuff, but it's the same equation I have down here. They just write the right side of it. Okay, and so that way you can get a nice chart where everybody knows what trend line you're looking at. Okay, all right, so that's it for making a trend line in this. Sometimes you just want the information, the slope and the intercept, and sometimes you actually want to graph it. Let's do one thing with this slope and the intercept before moving on to the next idea. Let's see how we can use this trend line. So for instance, I might want to know, might want to predict what is the chirp rate at 95 degrees Fahrenheit, right? So I don't have any data there. My data stops a little bit below that, but I can use this formula. I take C equals 0.203. I put in the temperature, 95, and then I add 0.459. And what I get is, let me type this in, I get 0.203 times 95 plus 0.459. And I'm getting 19.74. Okay? And that's it. That's now that does not mean that's exactly what's going to happen. What we can see is, right, that this trend line does not always hit the data. In fact, it might not hit any of this data exactly. The dots are big, so sometimes it hits it, but it's not actually going through the points that this data represents, right? But it's probably a good approximation. Looking at this line and how close it is to all of our data, I feel reasonably confident that, right, my data, if I went out to measure, would probably be somewhere nearby, right? Maybe between these two bars. I'm just eyeballing it right now, but we would have a reasonable approximation to the chirp rate at that temperature. Okay, all right, let's clear the drawings. I want to notice one more thing. There's this R squared box we can check. Right, and notice that R squared now appeared on the chart right here. Okay, let's talk about what this number is. All right, so we'll come back to this chart in a couple of minutes, but let's talk about this R squared value. All right, let's go back to a whiteboard. All right. So what did we look at? We saw that sometimes our data, here's some data that looks very linear. meaning it looks like drawing a line is a pretty good approximation to it. Here's some data. You have to squint your eyes a bit more to see that maybe this line captures the way that data moves, right? It doesn't look as, this looks a lot more reasonable an approximation to this. I know I'm just kind of, this is pretty rough, but I just want to get this idea, right? So not all data is going to work as well for this or be able to be described with a linear relationship as well. So what I'm describing here is how strong is the correlation, right? How well, we can think of it as how well is this linear model actually predicting the way whatever the two things we're talking about behave together, right? Sometimes it's going to be very well and sometimes it's not going to be so much, but we want a way to measure this. And what most people use, or what we're going to talk about here, is we can compute, we can measure the correlation with what we use the symbol R, which is called the correlation coefficient. Okay, so again, this is a computation that we're not going to go through. It's a complicated computation, but we do need to know what it means. Okay, so first of all, R is always going to be, between -1 and 1. Okay, so let's draw a little number line here. Here's -1, here's 1. Let's put 0 in the middle. If you get a correlation coefficient, right, which you'll use a computer to compute, if you get -1, it means perfect negative correlation. In other words, all the data lives on a line, and that line has a negative slope, right? Perfectly on a line, and the line has a negative slope. It does not mean the slope is -1, it just means the slope is negative. But what's important is it's saying they lie perfectly on a line. This will almost never happen in the real world. In a similar way, a perfect 1 means a perfect positive correlation. Okay? And 0 means no correlation. Okay? So in the middle, you're between a perfect correlation and no correlation. If you have an R value in here, for instance, it means you have a medium strength positive correlation, right? So your data might look, let's do examples of some just by eyeball. If I had data that looked, sorry, let me make this a little bigger. Let's go over here. If I had data that looked like this, right? I'm not seeing a line there, right? The data is all over the place. This would be an R value close to 0. If my data looks something like this, right? It looks a bit more like a line. It's not super strong. Let's say here, R is going to be somewhere in the middle. I'm going to write R is approximately 1/2, right? Just meaning it's a weak correlation. There's a little bit of a line you can eyeball here, but it doesn't seem all that strong, right? So it's going to be somewhere in the middle. And then we see correlation something like this, right? That looks much stronger. Some of the data we looked at looks like this, and you're going to get an R close to 1. okay? Same thing in the negative direction, except the slope is going to be down. This data will be slanting down instead of up, but the same idea. The more spread out and kind of off the line it looks, the less strong the correlation is, okay? So we also have, and I'll show you how to compute this with sheets in just a moment, we also have r squared. We just take the number r and square it, and this is sometimes called the coefficient of determination. And we can think of this as the portion of the variation, or how much of the variation in the dependent variable is explained by variation in the independent variable. Okay, so we'll go and look at this in a moment, but let's just clarify this idea of r squared. Crickets and temperature, right? So I was mentioning before that while you're measuring temperature and measuring cricket stuff, cricket chirp rate, there's a lot of other variables at the same time. How windy is it? How many other crickets are around? How bright is the moon, right? All these other things might affect the chirp rate. And so while you're looking at changing temperatures each time you take a measurement, other things might be also causing variation. R squared is trying to say, every time you took a new measurement at a different temperature, there was a change in the chirp rate. How much of that chirp rate change is explained by the temperature? That's what r squared is trying to tell us. And it's you can think of it as a percentage. It'll be a decimal like 0.75 or 75%. And you could say 75% of the change is explained by temperature, the other 25% by other variables, okay? So let's go back to that sheet, and notice here we've now shown r squared is 0.692. In other words, according to this calculation, 69 point, maybe I need to make this a little bigger. Oh, I guess the type doesn't get bigger, but right here we have r squared equal to 0.692. Okay. Now, we might also want to compute r itself, right? We could take the square root is one way, but there's also a command correl equals correl, and notice this says, it's sometimes called this longer name, but you can see correlation coefficient here. Same thing as doing the linear regression. I need to put in the dependent data followed by the independent data. And I see a correlation of 0.832, which is a fairly strong positive linear relationship, right? 0.83 is pretty close to 1. It's positive, and that's what this image is showing me, right? That this correlation is both positive, and we can see it looks, just eyeballing it, it looks to be pretty good. None of those points are very far off of that line. If we go over to, let's share one more thing. If I go back to that femur data we were looking at, notice one second, it's a little bit bigger. This graphing software I use also computes, besides the slope and the intercept, it computes r squared and r for us. And again, here we see an even stronger linear relationship, 0.898 and an r squared value of 0.8064, saying that 80% of the variation in height can be explained by variation in femur length. Okay. Okay. All right. That is it for this one. Thanks, everybody. I will see you next time.